Afternoon students. So let's start today's class. It is depending on the last class we studied about standing waves in organ pipes. So there are a few numericals left that we'll discuss it, and then we'll go on to find the velocity of sound through resonance column method. Okay, so let us see, this is the question I have written. A tube of 1 meter length is closed at one end. A stretched wire of 0.3 meter long and has mass 0.01 kg. It is held fixed at both ends and vibrate in its fundamental mode. It sets the air column in the tube in vibration at its fundamental frequency. Speed of sound is given 330 meter per second. So what is happening in this case? There is one organ pipe closed at one end. Okay, that is going to vibrate due to stretched wire. Okay, and its length and mass is given to us. Okay, and what is we have to find frequency of oscillation of air column. Alright, so when the string is going to be the source and the pipe, the organ pipe is going to resonate with it, so that means both will have same frequency only. Okay, so we'll see what the data is given and accordingly we'll try to find. Okay, so length of the tube is given. Length of the tube is 1 meter. So length of tube, that means organ pipe, is 1 meter given. Okay, and it's a closed end, so it means it's a closed organ pipe. Stretched wire, the stretched wire's length is given. Length of wire is given 0.3 meter, and mass is given 0.01 kg. Okay, then it is held fixed at both ends. Find vibrate in its fundamental mode. Okay, now fundamental mode of wire, it's fixed at both ends, so we know that its frequency has to be V by 2L. Okay, and what is V then? V is root over T by mu by 2L. Okay, mu we know, L we know. T actually is the second question over here, so T also we have to find. Okay, let's go on to the organ pipe. What is given? Let's see. It sets the air column in the tube in vibration at its fundamental frequency and velocity of sound is given. So let's talk about the tube first. Okay, it's closed at one end. That means its fundamental frequency is going to be V by 4L. Okay, V is given? Yes, it's 330. So 330 here. Is length given? Yes, 1. So what is the frequency of the organ pipe? Organ pipe 330 by 4. Okay, so that's its 2 here. This is 165. 165 by 2, that is 82.5. 82.5 hertz. That's the frequency of organ pipe. We got it. Okay, second case is what is the tension in wire? Now we know that because this wire is vibrating with the same frequency as that of the organ pipe. So this frequency I can keep here also. Okay. So we will keep that frequency as 82.5 and we try to find it. So 82.5 here. Okay, 82.5 into 2L into 2 and length is given 0.3 equal to root over T by mu. T we are finding, and what is mu? Mu is mass by length. What is mu? Mu is mass by length. Let us see. Okay, mu is mass by length. Mass is given to us as 0.01 kg, I guess, and length is 0.3. That's mu. Okay, so that's the value of mu. Mu is mass by length. Okay, this value of mu we have to keep over here or here. Okay, so we'll keep it. Shift it over here. 82.2 into 2. 82.2 into 2 means 165 into 0.3 equal to T by this value of mu, 0.01 to 0.3. This is in square root. Okay, now we can solve this one. Okay, to get the value of T. So it will be 165 into 0.3 into 0.01 by 0.3 square root. That's the value of 50. Okay, it's a calculation that you can solve it easily. Now, that's our another question. What is that question? Let's see. The question is, when an open organ pipe of length 15 meter is placed with a closed organ pipe of same length okay, then they produce same frequency with tuning fork of 100 Hz. Find the harmonics of both organ pipes. It's a very easy question. So since the tuning fork is having 100 Hz, both these pipes also need to have same frequency, 100 Hz only. So if we talk about, let's say, open organ pipe. Now we know that what are its normal harmonics. We can say that is NV by 2L. And this N represents number of harmonics in it. Okay. So 100 equal to N into V. So V we can take it as, let's say, 330 by 2, and length is given 15 meter. Okay. So you take it as better as speed as 300. It will be better for us to for calculation. This is 30, this will become 10. So N also will come as 10 only. So 10th harmonic. For which pipe? Open organ pipe. But if suppose that we are going to do it for closed organ pipe, what is the formula? Say 2n plus 1 V by 4L. Now 2n plus 1 is number of harmonics over there. You can use N also, there is no problem, because anyhow this is number of harmonics. So 100, this is 2n plus 1, taking this as 300, this is 4, and this is 15. Okay, so 4, 15, this will come as 5. So what are the number of harmonics in this case? This is 20. That means double of what we are getting for open organ pipe. Okay, so if these kinds of questions are coming, you need to be able to solve it. Okay, now let us go back onto the concept side. There is something called Rayleigh's criteria here. Okay, Rayleigh did one experiment and he found out that he concluded something that I am going to discuss with you. Rayleigh's criteria. Okay, what he said was, when we are talking about the standing waves in organ pipes, okay, so node is not happening right at the end of the pipe. It is happening somewhat above it. Okay, this side also and this side also. Okay, it's not happening right at the top or bottom of this organ pipe. It's happening slightly beyond it. For closed organ pipe also and for open organ pipe also. Here also like this. So this length, which is the extra length, he said is end correction. What name he gave? He gave this as end correction. Here also and here also for open organ pipe, and for closed organ pipe it's 1. Okay, so if I make one fundamental tone diagram over here, we know that this is a node and this is a node. We'll be making it like this. Okay, length of the organ pipe is this one. Same way here also I will make. Okay, this is length of the pipe. Now you can see that the separation between this node and this empty node is not L actually, it's L plus E. So for a closed organ pipe, you observe that the lambda by 4 is L plus E and not L alone. And here also, this lambda by 2 in open organ pipe is not L alone, it is L plus 2. So lambda in this case is actually what? 2L plus 4E, or you can say 2 into L plus 2E. So frequency in this case will be what? V by lambda, that means V by 2 into L plus 2. Same way here, lambda is 4 into L plus E. So frequency here will be what? V by lambda, that is V by 4 into L plus E. Okay, so here when we are using V by 2L for normal modes, here we are going to use now what? V by 2 into L plus 2. Here we were using V by 4L. So here we are going to use V by 4 into L plus. That we have to remember. But again, note it, unless it is mentioned in the question, we are not going to consider end correction. We will solve all the questions without end correction if it is not mentioned. Okay, and one more important thing, what is the value of this E obtained by Rayleigh? He said that E is actually 0.6 R. E value is 0.6 R. Now what is R here? R is the radius of these cylindrical organ pipes. Here R and this one R. Okay, so E value is 0.6 R. Remember that. So whenever if it's asked in a separate question, you should be able to give the answer of this one. Okay, and whenever end correction is given in a problem, we will be using this formula. Otherwise, we will be having same formula that we studied. V by 2L is a normal mode of frequency for open organ pipe, V by 4L for closed organ pipe. Okay, now let us see how to find with experiment speed of sound. Okay, that's called resonance column method. Experiment name is resonance column method. Okay, now in this one what we are taking? We are taking one closed organ pipe. And this closed organ pipe of some length L, we are filling with water. And we are taking one tuning fork of certain frequency. Okay, now this tuning fork we are going to vibrate. It's going to vibrate with this frequency, and here we are going to open it so that the water can go. What are we trying to do? We are going to observe the frequency of this organ pipe also. Okay, we will stop the outflow of the water when the frequency of this organ pipe matches with its frequency. That means both are in resonance. Then we will stop it. Okay, now we allow it to go it down. This water is going down. Now suppose at this position we stop outflow of the water. Okay, and we measure this length. Okay, at this position I got the frequency of this organ pipe is same as that of this frequency. Okay, I measured the length. Then what I will do? I know that this has to be the first frequency. That means first fundamental frequency. That means here will be node, and obviously here is empty. This is first fundamental frequency because you started with zero length for air. Always remember, whenever we say organ pipe, we are making the sound to oscillate in air, not in water. Water is other medium. Okay, so in air we are increasing the length of air column in this one. So we increase the length of air column and we got the first frequency. That frequency matched with the frequency of organ pipe, and we stopped its outflow. We measured this length. Now what we have to do? Now we know that this has to be lambda by 4. Okay, and this length is E. We will write at lambda by 4 equal to L1, we will say that. L1 plus E. We measured it. Now again we opened it. Now again the water is flowing. Okay. Then again at some other position, when it came down further, here we got the frequency again with the same tuning fork. Same tuning fork is being played. Again you got resonance at this position. Now what is happening? Now this is the next frequency. This is first harmonic. So this will be the next, that means third harmonic. So how will that be? Like this. This is third harmonic. Okay, we'll again measure this length. Let's say that's L2. Okay, and we know that this actually is how much? This is lambda by 2 and this is lambda by 4. So this will come 3 lambda by 4. Okay, what we'll write then? Say 3 lambda by 4 equal to L2 plus E. Okay, these two equations we got. Now we'll try to remove this E from here. Okay, so what we can do? We can subtract first equation from the second equation. We add it now. This is gone. Here I am getting L2 minus L1 and here 3 lambda by 4 minus lambda by 4. That means 2 lambda by 4. That means lambda by 2. Okay, and this lambda we can write as velocity by frequency because we have the formula as speed equal to frequency into wavelength. So see then further. This we can write lambda equal to 2 into L2 minus L1. This lambda we are writing as V by frequency. So this V value we can write as V equal to 2F into L2 minus L1. You measured L2 value already over here. You measured L1 value already over here. Frequency of the tuning fork we know. So hence we can easily find what is the speed of sound through resonance column method. And on this resonance column method, definitely the questions used to come. Okay, what they will give us? They will give us the two lengths, they will give us the tuning fork frequency, and they will ask us the speed of sound. Okay, so that's it as far as organ pipe are concerned. The next topic that we are going to start is beats. Okay, that will be in the next class. Thank you.